just because look, my battery's almost dead.
Yes, yes.
But-
Let me. Does it have? Okay.
A USB, yeah.
Yeah.
Okay, let's see. I got enough space on the SD. Okay. It's recording.
So you got the camera?
Yeah.
What is this?
It's just my little.
Is it a GoPro?
Yeah, it's kind of like a GoPro.
Yeah. We should buy this, right?
Yeah, this was from. It's a Firefly. It's a $70.
That's it?
Yeah, yeah.
And then we will upload this video to the official YouTube channel from my computer. So we
Oh,
don't
I
need-
see. So it's not currently.
I'm not sure if it's. I think it could stream live, but I think we need to use another software or something.
Yeah, we
But
need a software. So
Okay, let's just.
But yeah,
And it has
it's recording.
quality.
Oh, this is excellent quality. We'll see. But yeah.
What are we doing?
yeah, I know. But this, I mean, the things that we don't know if this can stream live. The problem, the limitation is that we need to stream live.
Right.
That's
Yeah, I haven't played with that enough. I think it is because it's a GoPro. It's meant for like
It's just
stream.
$70.
Yeah, and it's
Then
got
I
all
can buy
kinds
a
of.
few of these.
Yeah, it's got all kinds
yeah.
of
Well,
cool things.
let me. I can work with him and see if that works.
Okay.
I don't want
Otherwise-
either of you to waste your time on this, but
Yeah, no, it's
any
not a
time
waste
that
at
you
all.
offer.
Yeah, yeah, sure. I just had it sitting.
Yeah, but that's more expensive, right? Okay, we'll figure it. Alright, class, let's get started. Seems like the class is getting smaller. This is not 160 people, right? I wonder if it has something to do with the fact that this is getting recorded. But, well. Anyway, so, for those of you who are here, welcome. You get to know about this. I mean, I'm sure you've seen this before. There's a lot of stuff that's due. I'm sure you're busy. There's a homework that's due next Tuesday. Learning theory, and I've had many interesting questions about this. I haven't had a chance to look at Canvas since yesterday, so I don't know if there was any more discussion. Are there any questions about the homework? Yeah?
So, on the very first question, it talks about like building the product by combining any of the parts that there are.
That's right.
Is there is that like with replacement? You know, like
No,
once you-
no. Once you use the product, you use the product. You can't combine it with.
Well, I'm saying it's like parts, and like in my mind, I have a bucket of parts, so I can use that part. So you're saying it's just like one of each part,
Right.
Motor, okay.
Yeah. Yes. You know, I never thought of that possibility until you brought it up. So, yes, everything gets used at most once. But in general, I would say for that question, I realize that there can be more than one possible answer depending on how, in some sense, you view the world. Whether things that are broken can be combined or not, depending on that, your answer will change. For example, so what I suggest is you write your assumptions and you reason. So, what I want to test from this question is really, I want you to kind of count in funny ways. That's really the point. And really, what I would like you to explain is how you arrive at your count. And if, while grading, we find that your reasoning is completely broken, you have invented new parts that don't exist, then we'll take away points. But really, I want you to do some combinatorial thinking. So write down any assumptions you may have in your answers. Any other questions about the homework? Yes?
So same problem, it's the third bullet point. We're asked to compute the number of variables. For example, HCC. Is the robot, are we looking at the hypothesis space of the robot or of the experienced worker?
Of the robot.
Of the robot, yes.
The experienced worker is the oracle.
Okay.
Yeah. Other questions? So there was some interesting discussion in my office hours about VC dimensions. And I'm not going to retell the whole thing, but I just wanted to mention this one part of that, namely how rigorous should your proof be? Your proof should be rigorous. And in particular, in general, all VC dimension proofs should have two parts to it. At least if you claim that your VC dimension is some number, say 17, you need to prove two things. You need to prove that it is at least 17, that's the lower bound, and then you need to prove that it cannot be 18, and that makes it 17. So you need to prove a lower bound and an upper bound, and if you miss one of these things, then we will take away points. But more importantly, if you miss one of these things, your proof is not complete. If you prove that your VC dimension is at least 17, then maybe it is 300. So you need to show both sides. And proving the upper bound could be a little bit tricky. I want you to revisit how we did the same thing for linear classifiers, for example, or for all those other examples that we worked out in class. We will expect a somewhat rigorous proof. Another reminder about your project intermediate status report. The submission thing on Canvas is open now, so you can submit something now if you want, but after class. I've spoken enough about this that I don't feel like going over the whole thing again. One thing I did want to mention is for the competitive project, people came to me after class last time and asked, okay, can you tell me what all algorithms we have so far? And I thought I'll just list them out because this is not even the announcement I wanted to open up. That doesn't matter. So I thought I'll list it out by going over all the algorithms we've seen because I feel like you've seen a whole bunch of things and you may not realize it, but at this point you have in your toolkit at least about 8 different algorithms. So you have precision trees and say maybe with possibles plus depth limit, and then you have a perceptron. And just for the sake of the project, I'm going to argue that the perceptron and the margin perceptron are really the same thing. Because the perceptron is basically the same as the margin perceptron with the margin 0. So, and then you have averaging. In particular, you saw this averaging being applied to perceptron, so you get the average perceptron. But in theory, you could apply the same idea of averaging to SVM, for example, where you maintain an average vector and return that. And people don't do that normally, but you could try it. In fact, when I was a student and I was trying to figure out how these things work, I remember opening up some SVM library out there and finding, to my surprise, commented code that does averaging. So this was a person who basically invented a whole bunch of this stuff, and they didn't know. He was not sure what was going on, so he wanted to try out everything. One of the things he tried was averaging. Now, the interesting thing to keep in mind is averaging for SVM does not do much. Averaging for perceptron gives it generalization. For SVM, we get generalization because we have the margin anyway. So SVM comes pre-equipped with a way to get generalization. Averaging is not really needed, but you could try it. We did not see any other online algorithms, so then we moved to, what did we see after that? SVM. Oh yeah, we saw PAC, but I'm just listing out algorithms that you can actually use. And then we, your toolkit really gets bigger once we come to ensembles. So we saw boosting. I'm going to list boosting and bagging separately. You can, because now you can combine these two things and you get boosted decision trees or decision stumps. You can combine these two things and you get boosted perceptron. So you can combine these two, all of these. Similarly, you can combine these two things and you get something like random forest or bagged random forest and so on. So now, in some sense, these two are your enhancers. They can multiply with everything and they grow what you have. Just a preview of, I'm going to erase all these lines. So you saw boosted decision trees, you can have random forest, or other ways of making ensembles. You can have ensembles of decision trees that are learned using a perceptron. And maybe in your next homework, we'll have something like that. In addition, you can also have, what we're going to see coming ahead, just so that you can plan your, for your status report, you can, one thing I want you to list out is what other things you want to try. What else we will see that you will actually, that are implementable is naive Bayes, which we'll start looking at next Tuesday, and then logistic regression, which if I'm particularly ambitious, I'm going to say next Thursday, but we'll see how it goes. And then I'll introduce neural networks, but I will not cover neural networks in such depth that you'll be able to implement them. I want to introduce the concepts of these things. Neural networks are like a monster in the sense that there's hundreds of different possibilities. Like it's almost like Lego at some point. You mix and match and you get different things. So I want you to understand the philosophy of it and the math of it, because it's basically the same math that works everywhere. But I wouldn't expect you to implement it. If you want a particularly engaging weekend, let's say, I would encourage you to try implementing back propagation. It's a interesting exercise, but I'm not going to insist on that. But then at the end of the semester, we'll see nearest neighbors. And the reason I put that at the end is because honestly, this is the easiest learning algorithm we'll ever see. And so we'll need like, 10 minutes to cover it. And we can take maybe a few weeks to even analyze it, but we won't. So this plus neural networks, which I'm just going to put inside a box because I won't talk about implementing that, will be roughly what we'll cover. And if you notice, we've covered most of these things. So at this point, you have most of these things that you need. Pick 6 of these or 5 of these for your homework, for your exploratory project, and the 6th one can be anything. You can use a library, you can use TensorFlow if you want, or you can basically pick another one of these. It doesn't matter. So the question that came up was, I feel like we don't have enough algorithms to cover 6. I think we have more than 6 because these two can combine with a lot of these other things to get you more. so that's about the algorithms. I just wanted to make, was there a question? Quick announcement about a talk today. Ben Peepers from Michigan is going to be giving a talk at noon. Clearly, these slides are from last week. I hope something. Okay, this is today. So he's going to talk about robots and making them ethical and so on. But really, I just wanted to mention that we are truly fortunate that he's visiting us. He's a star in AI. He's been doing this for quite a while, and I strongly encourage you to be there. If the fact that he's there doesn't encourage you enough, there's pizza. I was told today that it's not 11:40, but 11:45. You want to time it just right. But anyway, but seriously, these talks could be particularly insightful because these are the kind of discussions that we should be having. He's going to talk about the ethical aspects of robotics, and we are at a point where we need to have that conversation. We are at a point in society where we need that conversation, and hopefully this will, give you some food for thought. So please try to be there if you can. I know there are classes that kind of end just before or just after the talk starts, so see if you can make it. All right. Today we're going to talk about a very brief but a very brief exploration into this topic called the bias and variance trade-off. And I was planning on not covering this in the first place, but I just thought I'll introduce you to this just to put these thoughts in your mind, because sometimes people use the language of bias variance trade-off to reason about why their classifiers don't work, and so it's a useful thing to it's a useful terminology to have. So let's talk about bias. So maybe even from the first lecture of the semester, I mentioned that learning is impossible if you don't make any assumptions. Anytime you're trying to learn something, you make some assumption about the hypothesis space. Maybe you'll assume that your model is linear. You'll assume that your true function is, what did I have here, a decision tree. We did not cover kernels, which is, as I probably hinted at before, a big disappointment a personal disappointment for me. But we'll see if we can do that. But there are things called quadratic kernels. Quadratic kernel, if you want a loose version of that, it's basically assuming that your feature transformation is all quadratic terms. Think of it that way. So even when you brainstorm feature transformations, essentially you're brainstorming assumptions about the true function. You believe that the true function is built out of these things. So every learning algorithm requires assumptions, but it's possible that given the set of assumptions you've made, given the hypothesis space that you have, no function is good enough. No, every function within the set of functions you consider is not particularly great. So you can ask, what is the error of the best classifier within your hypothesis set? Because that's like an upper limit. You cannot do better than that in terms of performance. So the bias is the generalization error of the best classifier in your hypothesis space. So quick humbling is what the statistical analysis of ensembles, not from the computational point of view, but from the statistical point of view, the reason why ensembles work is because they reduce variance, because you're combining multiple classifiers and the averages tend to be more robust. Bagging and boosting do that. If you reduce the depth of a decision tree, what you're doing is that if you reduce the depth, you are basically making the function space smaller, so you can increase the bias. If you increase the depth of a decision tree, as the depth increases, the bias reduces because you can represent more things. But the variance increases because you can represent more things, so you can overfit more things. For SVMs, higher degree polynomial kernels, or if you want for linear classifiers, feature transformations with higher degree polynomials can increase the variance but reduce the bias because you can represent more things. Regularization increases bias. If you increase the regularization, you increase the bias because your increasing regularization is making the classifier simpler in some sense. And we know how it makes it simpler. It makes it simpler in terms of VC dimensions. Increasing regularization reduces the VC dimension. So we'll see k nearest neighbors at the end, so I'm not going to comment on this right now, but general answer is if you increase k, bias increases. So questions about this stuff before we switch tracks?
What defines high and low on these?
Everything is relative to what you want. There is no absolute high and low. Okay, there is an absolute low, 0. It depends on what you would like from the data, from the model. So this is something that, again, I'll touch upon at the end of the semester. We talk about all these algorithms and we talk about how we can minimize error, loss, bias, variance, and all these things. But the truth is, what is useful depends on the application in which they're used. Maybe I work in a domain where a 70% accuracy is good enough. All I need is something slightly better than chance. Maybe 51% is good enough. Maybe I'm a hedge fund manager where all I need is a slight advantage over the competition. On the other hand, maybe I'm diagnosing diseases and a 99% error means 99% accuracy means I kill 1 in 100 people. So it totally depends on your application. So and this is something I'll spend a bit more time talking about at the end of the semester. So this semester we spend a lot of time talking about machine learning, and that's the center of the universe here. But there is some merit to thinking about the context, and that kind of often guides where our thresholds are. Alright, so quick summary about bias and variance. It's just a different view of learning criteria if you think about it. One could argue that we can, in fact, there are methods, especially in regression, where learning criteria are invented by saying, I would like a classifier or a regressor set of parameters that tries to reduce bias and variance. Or I would like a set of parameters that balances bias and variance in some way. And this intuition can be formalized just like we formalized the pack to give us something like SVM. So it's another, the bias variance analysis is another style of asking, is my learning algorithm successful? And another way of inventing learning criteria. And what ends up happening is the learning criteria that get invented through this style of analysis look extremely similar to the learning theory sort of criteria because in some sense they are trying to hit the same ideas, the same underlying points. So we don't get too different of an analysis from the bias variance methods. But it's just language that you should be aware of, and so if someone asks, you know now. Okay, are there any questions about this, or we're going to switch tracks and move to something else? In fact, something very different. Okay, that's an overwhelming vote for different. We're going to talk about Bayesian learning. This is, in my mind, Bayesian learning is like the third pillar that supports this class. So far, if you think about it, we've really been doing the same thing. We've been asking the same questions. What does it mean to learn? What does learning, what does success mean for learning? And we keep answering this question in different ways. And different styles in which we answer this question gives us different learning algorithms. It gives us different analyses. We've looked at online learning or mistake-bound learning, where we say learning is said to happen when the classifier or the predictor gets better as it sees more examples in a sequence. Especially in mistake-bound, the way we define learning is said to happen when the learning algorithm stops making mistakes. So we count mistakes as the criterion for success. We looked at pack learnability, where we defined, another way of looking at success. Namely, we want classifiers we want learning algorithms that, with high probability, produce classifiers that have low error. This style of reasoning gets us algorithms like SVM and AdaBoost and such things. In all cases, the learning algorithm is an algorithm that produces a function that can label new things. That once learning is done, we have a function at hand that can produce labels for new inputs. We're going to ask the same question in a different way, or we're going to ask the same question and answer it in a different way. Another way of thinking about what it means to learn is from a Bayesian perspective or a probabilistic perspective. And under this regime, again, we are going to invent or look at different learning algorithms. In particular, we'll look at the details of the naive Bayes and logistic regression. But in some sense, this is a much bigger thing. Bayesian learning gives us another recipe, just like loss minimization. Bayesian insight gives us a recipe for inventing learning algorithms. And what I would like you to take from this section of the class, not just today, but the next few lectures, is how do we distill these criteria for learning into a method for inventing learning algorithms. Because at the end of the semester, what I would like you to take home is not just, I know 8 different learning algorithms. What I would like you to be comfortable with is the ability to invent a new learning algorithm or use reason through this process of inventing new algorithms, because that's roughly what you'll end up doing, and we have mechanical ways of doing that anyway. So today, hopefully, we'll come to the end of this. I'm going to talk about what it means to be a Bayesian. In fact, it's almost like a philosophy. And then there is, we'll look at the 2 different criteria that we have within Bayesian learning. At least there are many criteria, but the 2 most popular ones are called maximum a posteriori estimation and maximum likelihood. Have people seen one or both of these things before? If you've taken some version of statistics or something like that, you would have seen maximum likelihood, for example. I'm going to instantiate especially maximum likelihood estimation in 2 specific applications, just to show how we can, in some sense, invent learning algorithms from scratch. And then the next lecture, we'll look at naive Bayes, and then we'll look at logistic regression. So let's start off with Bayesian learning. Before going into the details of Bayesian learning, I want to kind of introduce this sort of a caveat about 2 different things that you might hear when people say probabilistic learning. There are 2 different notions of probabilistic learning. One of them is the idea that you learn probabilistic concepts. Your hypothesis space no longer consists of functions that produce labels, but your hypothesis space consists of functions that produce probabilities. So a hypothesis space is a function that maps instances x to the range 0 to 1. And you interpret that range, the output c of x, as a probability that the label is 1. It's just you're not learning a decision function, but you're learning a probability. This this perspective, where you learn probabilistic concepts, it turns out can be analyzed using basically the same sort of analysis technique that we've seen so far, with some minor variations. Going ahead, that's not what I'm going to talk about. Another thing that people say when they say probabilistic learning is more correctly or more commonly called Bayesian learning, where the criteria that's used, the criterion that's used for selecting what is a good classifier itself is driven from basically applying Bayes theory. The function that you are selecting could be a Boolean function, like the functions that we've seen before, conjunctions and such things. So you could ask, what is the best classifier given a certain data set? You can define best using a probabilistic criterion and go follow through with whatever the math tells you. So the criterion for selecting the hypothesis is probabilistic. Now, these two are different. Here, in this, on the top, the function that's being learned is a probability. At the bottom, probability theory is used to discover hypotheses. Now, it seems like, I hope these two are, the distinction is clear. Is the distinction clear? Does the difference make sense? Yeah?
So is it like the first one is a function that assigns a probability?
That's
and
right.
The second one assigns a probability to functions?
That's right.
Is that-
That's exactly right. In fact, I couldn't have put it more confusingly myself. The first one gives you functions that assign probabilities. The second one gives you probabilities over functions. Now, I like what you said because I can continue that second sentence. The second one could be a way of assigning probabilities over functions that themselves assign probabilities to instances. Right? And that can get confusing, but that's exactly what we will do when we come to naive Bayes and logistic regression. And the reason I'm giving you a heads up is because every single step that I will take in getting there would seem obvious, but somewhere along the way, people tend to get lost. So just keep this difference in mind. Let's start simple. Using the same sort of terminology that we saw before, we need to find the best hypothesis. Our goal is to find the best hypothesis given a data set. We can define best in many ways. We can define best as the hypothesis that makes the fewest mistakes. In Bayesian learning, we're going to define best as the function that is most probable given the data. The most probable hypothesis in your hypothesis space is going to be the one that you like the most. You can define best that way. But for that, you need some way of assigning probabilities over functions. You need some way of saying this function is more probable than that. So we need some probability over hypothesis. And we also need to make some assumptions about how the data connects to the observed data connects to the hypothesis. Because we only have the data at hand, and we need to assign a probability over hypothesis using the data that we have. Like I said, we can be Bayesian about other things. We can be Bayesian about the parameters. We can be Bayesian about prediction, and it's almost like a one-shop stop. You can be Bayesian about everything. And there are people who spend their entire careers basically inventing and refining Bayesian criteria for all sorts of things. Like I said, it turns out that there are multiple roles that Bayesian analysis provides. You can have practical learning algorithms. Some of the most commonly used learning algorithms today have their roots in Bayesian analysis. And another sort of important idea that comes up in multiple places but becomes very obvious once you are thinking in a Bayesian perspective is it gives you a formal way to combine prior insights that you may have about the model, about the hypothesis, with what the data tells you. So if you believe, for some reason, that most emails that you get are spam, suppose, and then you want to find the best classifier that respects that belief, how do you do that? It turns out, if you are Bayesian, you can actually encode that belief in a formal, mathematically correct way, and everything will work out. And we'll see that, how we do that. In some sense, this is a conceptual framework for reasoning about functions and data and about probabilities in general. And it gives us also tools for analyzing learning. But at the heart of all this is the Bayes theorem. It's my fond hope that all of you have seen Bayes theorem before, but I know that's not the case. So I'm not going to ask you to raise your hand if you've not seen it, but this is the Bayes theorem. You may have seen it, but you may not have kind of thought much about it. Maybe you saw it in a class sometime and yeah, whatever. So we have random variables, x and y. This is really shorthand for you have these variables, random variables x and y. The Bayes theorem says the probability, so let's just walk through this terminology. for this, and I will never use the thing at the bottom because it's just too many things to type, and most people don't use it. So what it says is, let's say you have observed X, you have seen X, and this is asking what's the probability that Y takes a certain value. Y takes a value Y, little y. And the Bayes theorem, this might be the oldest paper I have ever cited. It's from 1760s. The Bayes theorem is a fundamental truth. It tells us that, oh, by the way, if you want a fun read, you should check out the original paper that Thomas Bayes wrote. There is no math in it. Even the fonts are funny. The symbols that we use for the English alphabet were different at that time. Anyway, so the Bayes theorem says that the probability of Y conditioned on X, meaning conditioned on having seen X, is simply it's proportional to two things. It's proportional to the probability of X conditioned on Y times the probability of Y divided by the probability of X. I'm sure you've heard that version before. Let's think about what this means. Probability of Y is it's called the prior probability. It's saying, what's your belief in Y taking on a certain value before you see any X? This is like what I said before. Before I see an email, do I believe it's spam? These days, apparently, yes. So it's just your belief in the random variable Y before you do any sort of conditioning. Probability of X given Y is called the likelihood. What's the likelihood of observing X if this particular certain Y is observed? What's the probability of observing these words in my email if it is a spam email? What's the probability of observing these words in my email if it was not a spam email? And the thing on the other side of the equality is called the posterior probability. The posterior probability is after having observed X, what's the probability over Y? So Bayes' theorem simply says the posterior is proportional to the likelihood times the prior. And this is something that I will be repeating multiple times. The posterior is proportional to the likelihood times the prior. Let's say, and almost in most cases we'll be ignoring the denominator, but unless, as far as this class is concerned, in fact, as far as this semester's class is concerned, we'll probably ignore the denominator in all cases. There are some cases where the denominator becomes a nuisance, but we'll not touch any of those cases here. So the posterior, in some sense, the important part of Bayes' theorem is that the posterior probability of having seen the of observing Y conditioned on some example on some X is proportional to two things. It's proportional to the prior belief times the likelihood. So both of these things could influence the posterior. So any questions before we continue on this? Here X and Y are just random variables. And one of the things that will happen is that once we get into the thick of things, we'll pretend that everything's a random variable. A data set's a random variable. A hypothesis is a random variable. The parameters, the weight vectors are random variables. Everything's a random variable, and we'll be continuously applying the Bayes rule. And we'll be now, the advantage of working within a probabilistic framework is that we have certain rules that we have to live with. By agreeing to work with a probabilistic framework, we are also agreeing to live with certain rules because we have probabilities at hand. In particular, we have these kind of rules. Probability of A and B is sometimes written as probability of A comma B is just probability of A conditioned on B and the probability of B. Probability of A or B, it's also called the sum rule, is probability of A plus probability of B minus the probability of the conjunction, which is this thing here. Also, we will extensively use this idea of independence. Two events are said to be independent if the probability of the union is the product of the probabilities. Probability of A and B is equal to product of A times probability of B. And that's the definition of independence. I'm sure you've seen this before, and I'm sure I'm embarrassing you by even going over this right now. There's a theorem of total probability which we'll probably use at least once, which says, say you have the probability of some event B. Now, I'm going to simplify this without all the math, but really, I can say, let's say there are some other event A. I don't know how A and B are related yet, but A can either be A1 or A2. Only these two things are possible. Meaning this the probability of A1 plus probability of A2 equals 1. These two things are the only things possible, and they are mutually exclusive. And then I can write this quantity here as probability of B is probability of B given A1 times probability of A1 plus given A2 times probability of A2. Basically, the first row says, this one here, says B can happen either when A1 happens or when A2 happens. So I can ask, what's the probability that B happened when A1 happened times the probability of A1 plus B happens when A2 happens times the probability of A2. But I can extend that to n things, and that's what you get here. The probability of B is sum over all n things of probability of B given AI times probability of AI. Once again, I'm sure you've seen some version of this at some point, or I hope you've seen some version of this at some point. If not, there are resources on the class website of the resources page where you can kind of refresh your memory. Yes?
Remember on the prerequisites.
Yes.
This is actually one of the questions.
That's right. This is the reason this is a question is in the prerequisites is because I assume that you have seen this and we'll build on top of this. That's exactly it. But then, if I remember right, there was also a question about convexity on the prerequisite quiz. So, calling it prerequisite may have been a little But anyway, so let's go back to Bayesian learning. Now we are all experts on probabilities and the Bayes theorem. So, we want to know what does it mean that a certain hypothesis is the best hypothesis for a given data set. And the criterion that Bayesian learning starts off with is the idea that we want the hypothesis that is the most probable, given the data. If you want to put that using the notation we've seen so far, we want a hypothesis, H, that is most probable conditioned on having seen this data set. So really, the conditional probability of the hypothesis given the data set is the quantity that we want to maximize. Given a certain data set, we can ask what's the probability of seeing hypothesis H1 versus probability of seeing hypothesis H2, and maybe defining best using this thing. But in doing this, in writing it this way, we are making a sort of there's a mental leap that let me try to walk you through that. This quantity here, the probability of H given the data, of the hypothesis given the data. Remember, this is called the posterior, right? This is the posterior probability of seeing the hypothesis of the posterior probability of a certain hypothesis conditioned on the fact that we have this data set. What's the probability that we have this hypothesis given that this data set is observed? But the key insight here is both H and D are really events in the sense of the same way events are defined in probabilities. D is the event that among all the data sets that we could have possibly observed, this is the one that we observed. The one that we have at hand is the one that we observed. You can think of events, or you can define events however you want. D is an event that we observed this particular data set that we have. H is the event that some particular hypothesis H is the true function. So really, the posterior probability is asking, what is the probability that H is the true function conditioned on the event that we have observed this particular data set? Does it make sense? Any questions? So this is, I could have written this as, just of y conditioned on x. Just like I did before, where instead of y I have this and x I have this. But the nice thing here is now I can apply Bayes' rule. I can apply Bayes' rule and I can just blindly apply Bayes' rule. Probability of h given d is simply probability of d given h times the probability of h divided by probability of d. This is just a blind application of the Bayes' rule, but let's see what this means. First, let's go back to the prior. The prior probability of h, P of h, is, it encodes background knowledge. It says, what do you believe the hypothesis to be before you observe any data? This is a term that allows you to introduce or inject your beliefs into the learning. So if I believe that most emails are spam, I would give higher prior probability to classifiers that label emails as spam. So in the absence of any information, what do I believe? Some classifier is the best, is the true one. Oftentimes, we have so little information that we have no way of picking one classifier over another. Meaning all hypotheses are equally possible. It's equally possible that all functions are the true classifiers before we see any data, in which case we have implicitly introduced the belief that the prior probability is a uniform distribution. Everything is equally likely. So we get to choose a certain probability. If you don't have any reason to pick one over the other, pick the uniform distribution. The likelihood term, probability of t given h, is asking what's the probability that this particular data set would exist if h was the true hypothesis. Among all data sets that could have existed, what's the probability that this particular data set could exist if a certain classifier is the true function? And then the denominator, P of d, is asking what's the probability of observing this data set. Doesn't matter what the classifier is. What's the probability that this data set would be observed? We will spend less time thinking about the denominator, so I'm going to skip that. But before we start teasing this apart, are there any questions about this particular? Yes?
We skip P of D because there's no way of knowing?
We skip P of D because we're going to maximize over H. So it gives.
So in like machine learning, D is basically can be my training set.
D is your training set. Yes, that's right. So in some sense, what you're asking is, the posterior is what's the probability that a classifier is a certain thing, given that you have this training set. The likelihood is asking, what's the probability that this training set would exist, given that the classifier is this particular thing. So it's kind of switching. Yes, so D is the training set. Yes.
So if we're assuming the prior is uniform, can we neglect it like we do the denominator as part of the normal?
We will end up doing that. Yes.
Just concentrate on the likelihood.
That's exactly what we will do, and that gives us maximum likelihood estimation. We will talk about that in maybe 5 minutes. Yes. I know there was some other hand, you pointed to a hand and then it disappeared. Okay. Are there other questions? So depending on how you feel about life, this is either extremely confusing or extremely obvious. I don't know, I feel like there's a very strong preference one way or another when it comes to Bayesian learning. Some people think this way, some people have to be forced to think this way. I would argue that this is a useful tool to have in your mental processes. You're the TA, you should know all the but no. Yes, yes. Okay, now based on this, let's now revisit the question of what it means for a certain classifier to be the best. There are two criteria. The maximum a posteriori criterion is nobody says maximum a posteriori because it's a mouthful, it's just map. Okay? The map hypothesis is the most probable one. What that means is the hypothesis that has the highest posterior distribution. What's the posterior distribution? It's P of H given D. So the learning criterion is you find P of H given D, you enumerate all possible hypotheses you have, and find the the one that has the highest posterior probability, and that's the classifier that map learning will produce. But we know that P of H given D is P of D given X times P of D blah blah blah. So I can apply Bayes' rule, go through the same analysis that we saw before, but I skipped 2 steps here, but now there's no surprises left for you. Notice that from here to here is just Bayes' rule. And the next step from here to here, can someone tell me why that's correct? Because P of D is a constant. Keep in mind, I'm maximizing only over the H. I'm enumerating all possible H's and finding the one that has the highest thing here. But P of D is just a constant because it's independent of H. I don't need to worry about it. So I can just get rid of it. The function, the hypothesis that maximizes the thing in the box would also be the hypothesis that maximizes this term. In other words, we are using the fact that the posterior is proportional to the likelihood times the prior, and we are finding the classifier, the hypothesis that has the highest posterior probability, and instead we are finding or equivalently, we are finding the classifier that has the highest product of the likelihood times the prior. So that's what the map criterion is. Now, keep in mind, notice that I have said nothing about any specific hypothesis class here. I've still kept H as just a set of functions, because this applies to no matter what hypothesis class you have. So you can have Bayesian criteria for learning decision trees. You can have Bayesian criteria for learning neural networks. Doesn't matter. It does matter because it changes what the likelihood and the prior will become, but you could define Bayesian criteria for any new hypothesis class that you have. Now, let's see what, let's kind of go into this a bit more. So, the map criterion, in order to find the map hypothesis, what do you need? You need to define 2 functions. You need to define a function called the likelihood, which says if which given a hypothesis tells you what's the probability of observing a certain training set. That's the likelihood term. And you need to define another function called the prior. The prior encodes your prior beliefs that this particular hypothesis is the true one. Now, there is we will get to this in a bit, but this is almost like a standard recipe for constructing the likelihood. And we will instantiate that at least 4 times in the next week or 2. But with respect to the prior, what can I say? I mean, it's your prior belief. It's how much you believe that how you believe the world works. That's one way of thinking about it. Another way of thinking about it is it's a way of injecting certain regularities that you want. This could be where you have your Occam's razor showing up. In the absence of any information, I want to prefer simpler classifiers. If you want to encode that, you put that into the prior. Yes?
So your prior belief directly influences what comes out of this.
Absolutely.
So if you have a really wrong prior belief, you're going to get a really wrong hypothesis.
Yes.
Okay.
Yes, and that's not just about machine learning. That's a truth.
I guess it's true about anything. Yeah.
Oh, as an
Nothing
aside,
wrong with data.
Yes.
Convincing.
In fact, if you were looking for a book recommendation, I would suggest reading Nate Silver's book, The Signal and the Noise, where he talks about how we can use Bayesian reasoning to do things like predicting which baseball player will succeed or who will win what elections. And if your prior is wrong, your predictions are going to be wrong. Right. And also that's a book that has fantastic examples for introducing this kind of stuff to lay people. Okay, so if your prior beliefs, you don't have any prior belief. If let's say you go into this thing and you say, I don't know what. At that point, you have the option of using a uniform prior. You can say all hypotheses are equally likely. So, given any two hypotheses, hi and hj, p of hi equals p of hj, which means you get the true function. Sorry, the function that's learned depends completely on the likelihood. It doesn't depend on the prior at all. And this is the question that you had asked before. If all your hypotheses are equally likely or have equal prior, then you can basically drop this term and you find a hypothesis that maximizes the likelihood. This is another learning criterion. So the maximum likelihood criterion is basically the idea that your best, this is another way of defining best, really. You define best above by saying the best classifier is the one that maximizes the product of the likelihood and the prior. Another way of defining the best is saying, yeah, it is the product of the likelihood and the one that maximizes the product of the likelihood and the prior, but the prior is all uniform. So basically the best is the one that maximizes the likelihood. That's called, thankfully, a much simpler name, maximum likelihood estimation. These are two different Bayesian criteria. There are a couple of others, but we'll not go into that. These are the two that we use quite a bit. In fact, I'll be talking about maximum likelihood estimation in a lot more detail in a bit. From a computational point of view, from a mathematical point of view, often we don't directly deal with likelihood. We end up dealing with log likelihood. So you'll see log likelihoods a lot. Very often, the first thing that we do when we derive the algorithms for maximizing these things is we take the log so that the math becomes easier. So we'll do that right now. So let me give you just to kind of get a sense of what this is. Let's talk about this brute force learning algorithm for map estimation. This is an algorithm that should not be called an algorithm. It's an embarrassment. What you do is you have a hypothesis space. The hypothesis space is just a set. It could have infinite things, but it's just a set. What you do is for every element of that set, you go and find this the posterior probability, this quantity here, and then you enumerate all of them and you find the one that has the highest. Basically, the way, if you want to think of it for decision trees, you enumerate every possible decision tree, calculate the posterior probability, and find the one that has the highest. If you want to think of it for linear classifiers, you enumerate every, oh, that doesn't work. Yes?
Every possible hypothesis.
Capital H? Yes, it's your hypothesis space.
So that is already a choice, right?
That's already,
A choice.
that's a choice, of course. Yes, yes, that's a choice. And that's the modeling choice, that we have to make that choice no matter what.
Can you throw that in probability as well?
You could.
That's a prime.
Yes, in fact, you can reason about that as being a prime by saying for all functions outside x, the probability is 0. So you can basically wrap everything you want into this Bayesian perspective. Yes, you can think of the choice of the hypothesis space itself as a prime. So this is just to get a sense of what we need to do to, for map estimation. But of course, this is a stupid idea. You're never going to do this because we only have a finite amount of time before the universe kind of burns into. So, if you are naive about this is going to be difficult. So this is where the algorithmic component of Bayesian learning comes in. We need algorithms that can do this maximization. Let me give you 2 examples of maximum likelihood estimation. Let's talk about Bernoulli trials first. Just to set this up, we are going to use see a concrete example of maximum likelihood estimation. In order for this to work, we need a task. We'll get to the task first. But once we have a task, we need to define 2 things. We need a hypothesis space, And we need to somehow define that the likelihood term of the given h. We need some model that says, here is how, if the true function was h, here is how the data d would be generated. So we need to define both these things, otherwise, well, we just have functions, we just have abstract functions. So let's make this very, very concrete. Let's say after this class you're going to do a consulting job, and some company that manufactures, what is it today, light bulbs, wants you to build some machine learning system that helps them detect whether a light bulb is faulty. What's the probability that a light bulb is faulty? And of course, you're going to be very rigorous about this, and you want to know if they are identical. Or actually, you want to know if they are IID, but you can't ask that to a random CEO. So you want to know if they are identical, and of course, they're going to say yes. And so at this point, you need data. To collect data, you perform an experiment. What you do is you try out 100 light bulbs. 80 of them work, and you say the probability of failure is 0.2. And the CEO, not having done much math, asks you why. At that point, you have to now give them a reason. Why is it 0.2? Why is the probability of failure 0.2? Sorry?
So posterior knowledge.
It's 20 over 80 plus 20. Someone else said something.
They're identical, so
They're identical.
they have the same distributions.
Yes.
If you're giving the sample, you should know that the true distribution should be the same.
But that's not a proof. Okay, you want to prove it?
So you can randomly, you can arbitrarily assume the probability is a real number between 0 and 1.
Yes.
And you start this. So you have 100 data points, and you fit your map on that 100 data points with your Bayesian equation.
In some sense, yes. I'm going to make it simpler. I'm going to argue that this 0.2, which all of you agree on, in order to come over what you said, 20 over 20 plus 80, what you have internally done is maximum likelihood estimation. You may not realize it, so let me prove it to you. Let's say that we have some probability. We don't know what the probability is. Let's call it P. Probability of success is 1 minus P. The probability of failure is P. Every trial is IID, independent but identically distributed. We have seen some data. We have seen data that says there are 80% of them, oh wow, colors are right. 80% of them are working and 20% of them are not, which means you can ask, what is the probability that we would see this particular data set if the probability of failure was P? Probability of seeing that particular data set is P power 80. Wait, I messed this up, didn't I? Yeah, but you know what I'm doing here, so let's call the probability of success. So it's given this assumption, it's P power 80 times 1 minus P power 20, but you could have chosen these 80 things in 100 choose 80 ways. So the probability of observing this particular data set is 100 choose 80 times P power 80 times 1 minus P power 20. That's your likelihood. Now what we have done is in just this slide, we have made a whole bunch of assumptions. First of all, we are assuming that these are Bernoulli trials, that the probability of a light bulb succeeding is just completely characterized by this one number. It's not dependent on any measurement that you take from the light bulb. It's just just this one number. That's the Bernoulli trial. We made an assumption that all light bulbs are independent but identically distributed. That's a kind of a bogus assumption, right? I mean, if the machine breaks down, a whole bunch of them are dependent on each other at the same time. But we are going to simplify our lives. And based on these assumptions, we are able to now, mathematically or write down in a functional form the likelihood of the data given this particular modeling choice that we have made. Well, now we can maximize likelihood and life is good, right? We have a function, we need to maximize this. We have this function, we want to find p that maximizes that thing. First thing you always do, just because it almost always seems to work out that way, is you don't ever work with the likelihood, you work with the log likelihood. Our goal is to find what's the maximum value of p. What value of p would have generated this particular observation, would have most probably generated this observation. So in other words, we want to solve this particular maximization problem. We want to find the model, the p that maximizes the likelihood, which is just this thing here. Like I said, let me just generalize this. Suppose you have A light bulbs that work and B that do not work. So we want to find the best probability, which is the maximum likelihood thing. Like I said, we are never going to work with likelihood, we're going to work with log likelihood. And what I've done here is just work through the math. So I'm not going to do everything in great amount of detail, but this is exactly the same thing that we saw before, just in terms of A and B. Taking log, the first term disappears because it doesn't depend on p, so we can ignore it. So it's really a log p plus b log 1 minus p. We want to find p that maximizes that expression. And at this point, you know how to solve it, right? It is, I think, something that you may have seen in 7th grade or something, where you take the derivative and set it to 0. So you can take the derivative of this thing, set it to 0. There's not much, more that I can say. Should I? Well, let's do it. A divided by 1 minus b divided by 1 minus p is 0, and at that point you just solve for p. Solve for p, and you get p equals b divided by a plus b. The probability of failure is b divided by a plus b, which was 0.2. So this is the reason. So we made, when you actually said the probability of failure for that example was that data set was 0.2, it's amazing because instantly in your head you made this model choice. You assumed that everything is IID. No, I told you everything was IID. You solved this optimization problem. You set up an optimization problem, you solved it in your head, you took the derivatives, and you told me 0.2. So, you made all these assumptions. You are a Bayesian. You solved the maximum likelihood estimation for this particular problem. We could have assumed other models. You could have assumed, instead of taking those measurements, you could have taken, the size of the light bulb. You could have, taken other properties of the light bulb, and you could have said the probability of failure is a function of certain properties of the light bulb itself. That's a different model. It could have been something like an exponential distribution or something. Or exponential family of models, something. So you assumed Bernoulli trials, and you also assumed that uniform priors. You assume that the p, all values of p between 0 and 1 are equally possible in the absence of any data. Notice that we did not have any trials because we did maximum likelihood estimation. We could have made other assumptions, but that requires you to redo the math. Questions about this process? Yes.
Is running QFD given H always going to be like in that form?
Which form?
Plus B, choose A.
No, it depends on the probability distribution. This is because it's Bernoulli trials. If you had a different distribution, in fact, we don't have time today. We'll look at the next, on next Tuesday, we'll look at an example of how we can do regression using the same sort of analysis. And you'll get a different way of doing the same thing. In fact, that's a good thing that you mentioned. In general, you have to do a few things. You need to decide on a hypothesis space H, which is in this case, you decided that essentially it is saying that what distribution it, how do you generate the data? These two are roughly the same thing. You need to define what is the task, and the second thing is what is the probability distribution for D conditioned on H. How is D generated? Often you don't usually look at the data set itself. You pretend that the data set D consists of many instances. It's a set. And you assume, the first assumption that you always make, because it's convenient really, is that every training example is independent, IID, and so the probability of D given H invariably always ends up being argmax over H, the product over all examples, let's call it XY, probability of X comma Y conditioned on H. Okay? So invariably this is always done. And then the other thing that happens is you take the log likelihood. So you take the log of this term, it becomes a sum, and then you solve for that. The other thing that to keep in mind, which is different about this example, is unlike what we will see later on, here I can actually set the derivative to 0 and get the answer. In practice, in most other cases, that's not possible. We won't be able to solve it, so we need an algorithm that actually does the maximization. We will need some sort of an algorithmic method for maximization. We may not be able to derive it in closed form. So examples of where we can actually do it in closed form would be naive Bayes. Naive Bayes is a classifier where we do maximum likelihood estimation and we'll be able to derive everything in closed form. So the learning algorithm for naive Bayes is literally just as simple as this. It's just counting. Where we won't be able to do it in closed form is logistic regression, where we'll have an optimization problem, argmax over some model, and that argmax, you can't just take the derivative and set it to 0. You could, but it's not computationally, it's not doable in a closed form. So we will need an algorithm. What we will do is we will reframe the learning problem as an optimization problem and then give it to an optimizer. In practice, what you will do is not give it to an optimizer, but you will give it to stochastic gradient descending. So we'll go back to that again. Okay? I'm going to stop. I don't want to start the next thing right now. On Tuesday, we'll pick up on, we'll continue where we left off. Oh, and don't forget the top name.
Mattia, right? Yeah.